Magandang umaga po sa lahat ng participants. Thank you for attending this webinar hosted by PICE. It is an honor for me to be invited as one of the speakers for this webinar. In this lecture, we will be talking about the analysis and design of moment connections in structural steel buildings of special moment frames, or what we call the SMF. These are the topics we will discuss for this lecture. For the first part, we will talk about the fundamental concepts. And on the second part, we will have a brief history of SMF connections. And for the third part, we will discuss some pre-qualified moment connections. These are the learning objectives we hope to achieve at the end of this presentation. First is to explain the fundamental concepts of steel SMF connection design. Second is to identify commonly used pre-qualified moment connections for SMF. And third, to familiarize design procedure and other design considerations. When we design for connections, NSCP references the AISC code. The primary reference for non-seismic or standard provisions is the AISC manual together with the AISC specifications. For seismic connections, AISC Seismic Design Manual and AISC 341 are the primary references, and AISC 358 is the main reference for pre-qualified moment connections. Now let's move on with our first topic of this lecture, the fundamental concepts that include the following: inelastic seismic response spectrum, fuse concept, ductility design concept, and capacity design concept. One of the fundamental concepts we need to understand is the inelastic response spectrum. As you can see in this slide, the elastic response spectrum is reduced by the redundancy factor R, in which the values depend on the level of detailing. We have special, intermediate, and ordinary frame. You might ask, why do we reduce the elastic response by dividing it by R? Well, the answer for that, it's very simple. It's for convenience, so that we don't have to do nonlinear analysis, which is very complicated. In other words, we just want to keep it simple. Another important concept is what we call the fuse concept. System quality is not only due to strength, but proportioning is the very key to a good behavior. In this picture, which circuit do you think is better? The 20 amp fuse with 25 amp max wire? Or is it the 30 amp fuse with 25 amp max wire? Fuses are all about proportioning to protect the elements. For a system with 20 amp wire, the 20 amp fuse is well proportioned to protect the system, whereas the 30 amp fuse is basically useless. As an analogy, seismic design is similar to a fuse concept. We proportion the moment frame structure to protect the columns from buckling. Let's relate the fuse concept to seismic design. The first seismic design concept is what we call the ductility design. A reduced design seismic force can only be used if sufficient ductility is built into the structure. However, only certain elements are strategically designed to deform inelastically. That is, the deformation controlled elements, or DCE. Note that in SMF, the DCEs are the beams. In this concept, we need to, number one, provide yielding elements to control overall force. It's basically to make sure the fuses are ductile. And second, to protect the non-yielding elements, that is to estimate the maximum force from the fuses. The second design concept is what we call the capacity design. In this concept, the remaining part of the structure is designed to remain elastic. That is what we call the force-controlled elements, or FCE. Note that in SMF, the FCEs are the columns. It is important to know that the quality of lateral force resisting system is not only due to strength. Proportioning is the very key to good behavior. Now, capacity design is an approach used to design structures for seismic resistance, in which the strength of the members comprising the seismic load resisting system are proportioned such that inelastic behavior is accommodated in specific designated locations that are adequately detailed to accommodate this behavior. When these elements yield, they limit the force that can be transmitted to other elements, and that's effectively shielding them from overstress and allowing them to resist design earthquake excitation while it remains elastic. This practice permits the elements that are not expected to yield or experience inelastic behavior to be designed and specified without difficult detailing practices intended to provide for ductile behavior. This is a matrix showing the effort needed for ductility versus capacity design concept. For ductility design concept, more research effort is required, but the design effort is straightforward. But for the capacity design concept, less research effort is required, but the design effort requires understanding or engineering judgment. This slide shows the areas where inelastic deformation in a steel SMF is expected. SMF is a highly ductile system where significant inelastic deformation in the form of plastic hinging in the beam section that is adjacent to the beam column connection is expected when subjected to severe cyclic loading. Panel zone, although it's difficult to predict, can contribute a significant amount of ductility to the frame. There are three basic approaches used that relate the strength and inelastic behavior of the panel relative to the strength and inelastic behavior of the framing members in the connection. First is the strong panel, where the panel zone strength is greater than the surrounding framing components to the point where the vast majority of the inelastic deformation occurs in the beam. Second is the weak panel, where the strength of the panel zone is low enough relative to the framing members such that the majority of the inelastic deformation occurs in the panel zone. And third is the balance panel, which falls between the strong and the weak panel. However, please note that AIC seismic provisions generally provide strong and balanced panel zone. For our second topic in this lecture, which is about the history of SMF connections, we will discuss the following items. First, we'll have a brief history of the pre-qualified connections. And second, we'll talk about pre-Northridge connections. And third, we'll be having a small discussion about the philosophy of AISC 341. According to history, the moment connections have evolved from riveted built-up columns and beams in the early 1900s to the welded unreinforced flange with bolted web in the late 1960s. But after the 1994 Northridge earthquake, it was discovered that a number of moment frame buildings experienced brittle fractures even for the moderate inelastic demands. Now, after that discovery, the SAC joint venture conducted extensive research and published a series of reports known as the FEMA 350 to 355 series. And following the SAC results, the concept of pre-qualified moment connections was subsequently incorporated into the AISC seismic provisions in 2002. These are the typical pre-Northridge moment connections that were widely used since the late 1960s, not only in California, but you can also see these in the Philippines even until today. But after the Northridge earthquake, it was discovered that these connections are fundamentally flawed. This slide shows the brittle fractures discovered after the Northridge earthquake. These fractures generally initiated near the CJP weld of the lower beam flange to the column flange. The first picture, it shows the fracture of beam flange at CJP weld of the beam flange to the column flange. The second picture, it shows the fracture involving a piece of steel that is being withdrawn from the column flange. And in the third picture, it shows the fracture extending through the column flange and the web. Note that these fractures are similar to the observed fractures in Japan after the Kobe earthquake in 1995. The current detailed design requirements for SMFs are referenced to the seismic provisions, or known as the AISC 341. Now, during large seismic events, SMFs are expected to develop significant inelastic deformation that is mostly in the beam plastic hinge that is away from the column face. Since it is more difficult to predict column panel zone deformation, AISC requires that at least 75% of the actual deformation must occur in the beam plastic hinge locations with the goal to achieve inelasticity through the plastic rotation in the beam. With that, AISC 341 adopted a performance criteria for SMF connections to develop a story drift angle of at least 4% without significant loss in the flexural capacity of the beam below 80% of its plastic moment capacity. And that should be based on qualifying cyclic test. Now, this requirement for acceptable strength degradation is illustrated in the hysteretic response curve shown on this slide. The behavior of SMF connections, especially the initiation and propagation of fracture, under severe cyclic loading cannot be reliably predicted by analytical investigation alone. Therefore, AISC 341 adopted a philosophy that performance of moment connections must be verified by laboratory cyclic testing on a realistic scale. Now, AISC 341 gives two options. The first option, the SER or the EOR, shall provide substantiating data either from project-specific tests or tests reported in recognized literature. Now, since performing such tests is expensive and time-consuming, a second option is provided to use the pre-qualified connections that is given in AISC 358. For the third topic in this lecture, which is about pre-qualified moment connections, we will discuss the types of pre-qualified connections, some pre-qualification requirements, an example moment connection called the reduced beam section or RBS, and one of the proprietary connection called the side plate moment connection. Shown on the left is the current AISC 358, which is the 2016 edition. It is the standard for the design, detailing, fabrication, and quality criteria of pre-qualified SMF connections that is in accordance with AISC 341. In this standard, there are 10 different SMF pre-qualified connections that is listed in the table on the right side, are provided with detailed step-by-step design procedure. Design engineers may choose between the 5 non-proprietary and 5 proprietary connections. When using the latter for building construction projects, engineers must obtain a license and work with the patent holders. Now, in this presentation, 2 different pre-qualified connections will be described in detail. The slide shows a reduced beam section, or commonly known as the dog bone connection. Please note that RBS is only pre-qualified for beams that are connected to the column flange and not to the column web. This one is a bolted extended end plate connection, and you have the option to use the unstiffened for lower moment demand and stiffened for higher moment demand. Please note that these are pre-qualified for beams that are connected to the column flange and not to the column web. This slide shows a bolted flange plate connection, which is very common here in the Philippines. Similar to RBS, this is only pre-qualified for beams that are connected to the column flange and not to the column web. This slide shows a welded unreinforced flange and welded web connection, which is very common here in the Philippines, but I doubt if the seismic detailing was implemented. Again, this is only pre-qualified for beams that are connected to the column flange. This one is the double T connection with the same warning. Again, this is for beams connected to the column flange. This is one of the proprietary connections called the Kaiser bolted bracket, or KBB. Another proprietary connection called the ConXTech ConXL. This is a very common proprietary connections in California. It's called the side plate. Another common proprietary connection in the US, it's called the Simpson strong tie strong frame. This proprietary connection is also very common in California, that is mostly used for retrofitting existing buildings. Before we proceed our discussion with the two common types of pre-qualified SMF connection, let's discuss briefly the common pre-qualification criteria. First is the member ductility requirement. The width to thickness ratios for the flanges and the web of beams and columns are proportioned for highly ductile members. On this slide, the limiting width to thickness ratios for both flanges and web of the wide flange sections are listed. Please note that this is different from the limiting width to thickness ratios given in the ASC standard specifications. Another pre-qualification limit is the protected zone. This zone in SMF is the location where plastic hinging of the beam develops that is away from the face of the column. In most pre-qualified connections, the listed items on this slide are prohibited. As you can see in the picture on the right, there is an unauthorized attachment within the protected zone of the dog bone connection. So to prevent that from happening, the EOR should show this typical detail in the design drawings. So the protected zone should be highlighted similar to the picture here. Another pre-qualification limit is the provision for lateral bracing of the beams. To avoid local buckling failure when subjected to excessive deformation, the beam is braced to satisfy the requirements for highly ductile members. Please note that for some connections, supplemental bracing may be required that is near the plastic hinge of the beam. For connections where the beam flanges are CJP welded to the column flange, this is the pre-qualified dimensioning of the weld access holes. Now, let's discuss in detail this very common pre-qualified connection. RBS was first introduced in 2005 version of AISC 358, but prior to its publication, this connection was already being used in a number of steel building projects and still very popular today. This connection is non-proprietary, which is pre-qualified for use in SMF systems. Now, the hysteretic response curve on this slide shows that RBS developed at least 3% of plastic rotation that is equivalent to 4% fifth angle required by the ASC 341. That is with the maximum moments at the face of the column that is greater than the 80% plastic moment capacity of the beam. RBS is fabricated by thermally cutting into a smooth curve the portions of the beam flanges adjacent to the column flange. This is done so that the formation of yielding and plastic hinges will occur primarily at the defined location within the reduced section of the beam. Now, as a result, the moment and inelastic deformation demands that is developed at the face of the column will be limited. In RBS, the protected zone is the area from the column face to the end of the beam section cut that is farthest from the face of the column. With this connection, the beam flanges are field welded to the column flanges using the CJP welds that must be detailed as demand critical. Similar to the beam flanges, the beam web is also CJP welded on the field. Now, since the performance of RBS is not highly sensitive to the geometry of the weld access hole, specific access hole geometry is not required. The RBS connection is pre-qualified for WF members up to W36 or W920 in millimeters, with weight limited to a maximum of 302 pound per foot. That's equivalent to 447 kilogram per meter, and a flange thickness of a maximum of 1¾ inch, or equivalent to 44 millimeters. For the column part of the SMF, however, weight and flange thickness are not limited. Please note, again and again, RBS is only pre-qualified for beams connected to the column flange and not to the column web. Let's discuss briefly the design procedure according to AISC 358. In step number 1, we should choose trial values for RBS dimensions A, B, and C. And shown on this slide are the limits for those dimensions. In step number 2, we should compute the plastic section modulus at the center of the RBS. And the equation is given also on this slide. For the next step, we should compute for the probable maximum moment at the plastic hinge using the equation given as MPR. For step number 4, we should compute for the shear force at the center of the RBS at each end of the beam. Note that the shear force at the center of the RBS shall be determined from the FBD of the portion of the beam between the center of the RBS. This calculation shall assume that the moment at the center of each RBS is the MPR and shall include the gravity loads acting on the beam based on the 1.2 D plus 0.5 L load combination. For step number 5, we should compute for the probable maximum moment at the face of the column. And in step number 6, we should compute for the plastic moment of the beam based on the expected yield stress. And in step number 7, we should check the flexural strength of the beam at the face of the column. For steps 5 to 7, the equations are given as MF, MPE, and MF. For step number 8, we should determine the required shear strength of the beam web and its connection using the equation below. For step number 9, we should design the beam to column connections as per section 5.6 of AIC 358. And for step number 10, we should check for continuity plate if it's required. And for step number 11, we should check for the beam and column relationship limitation as per section 5.4 of AIS 358. Now, let's discuss one of the most common proprietary connections called the side plate moment connection that is pre-qualified for use in SMF systems. The slide shows the field welded option, which utilizes redundant interconnecting structural plates, fillet weld loops, and high-strength pre-tension bolts to connect the beam to the column flange. One major advantage of using this connection system is that all welds are exclusively fillet welds, except for the flare bevel groove welds at rounded edges of HSS sections. Please note that in the US, the fillet weld is more economical than a CJP weld. I think it's also the same here because of the testing requirement for CJP weld. This slide shows the field bolted option where a cover plate, a pair of clip angles, and high-strength pre-tension bolts are used to connect the beam flanges to the side plates. The side plates are connected to the column in a similar fashion to the field welded option described in the previous slide. The beam web is connected to the column flange using vertical shear elements like shear plates or clip angles. Now, unlike RBS, side plate connection can be used in a biaxial configuration. It means that you can connect it to the column flange as well as to the column web. For over 2 decades, side plate connections have undergone nearly 40 full-scale tests. The test results have consistently proven that side plate connections far exceed the minimum requirements established by the code. Let me show you a full-scale seismic testing of side plate bolted connection, courtesy of side plate systems. Now you can see in the hysteretic curve that while the code requires 4% drift angle, this connection went all the way to 9%. Now recently, the latest resiliency compliance testing shows that side plate connections exhibit limited deformation at design level earthquakes. This has been independently validated based on the criteria set forth in FEMA P58, which is the current US standard for resilient design and risk assessment, both for new and existing buildings. This next video, courtesy of Side Plate Systems, shows a close-up view of a W21 beam and HSS 14 by 14 column being tested per ASC's protocol. In this specimen, 9% rotation was achieved with a bolted side plate connection. Since side plate moment connections are proportioned to develop the probable maximum moment capacity of the beam, the plastic hinge formation occurs within the beam. The side plates, in particular, are designed to develop a moment capacity larger than the plastic moment capacity of the beam. This is done to push the yielding and strain hardening towards the protected zone of the beam. The field welded side plate connection is pre-qualified for beams up to W40 or W1000 in millimeters, with weight limited to a maximum of 302 pound per foot and flange thickness of 2.5 inches maximum. For the column part of the SMF, WF sections are limited to W44, However, the weight and flange thickness are not limited. Now, the protected zone in this connection includes the beam area from the vertical edge of the side plate to a distance equal to 83% of the depth of the beam that is away from the column flange. For the field bolted connection shown on this slide, it is pre-qualified for beams not more than W44 with a maximum weight limit of 400 pound per foot and a flange thickness to a maximum of 2.5 inches. For the column part of the SMF, WF sections are limited to W44. However, the weight and flange thickness are not limited. In this case, the protected zone includes the beam area from the vertical edge of the side plate to a distance equal to 67% of the depth that is away from the column flange. With the side plate technology, stiffer moment frames can be modeled. This typically reduces the number of moment connections by 20 to 30% compared to the conventional moment frame buildings. You will see in this framing plan that only a pair of two bay SMF is required along the x-axis and three two-bay SMFs are required along the y. Additionally, the increased stiffness allows the design team to minimize the beam and the column weight by 15 to 25% of the lateral steel tonnage. There are other design considerations we need to check to complete the SMF connection. Similar to concrete SMRF, we need to check for the strong column weak beam. And to ensure adequate transfer of the couple force into the column, we need to check the panel zone shear. Now, if the column has insufficient capacity to transfer the couple force, continuity plates should be provided. And if the column fails in panel zone shear check, web Doppler plates should be provided. Before ending this presentation, let me give you this advice. Don't gamble on fundamentally flawed pre-Northridge moment connections. We have to use the pre-qualified SMF connections given in AISC 358. With that, I would say thank you for listening to my presentation.